this lesson I'm going to introduce some of the most commonly used equations in all of physics, equations that we'll be using all the time this semester. These are the kinematic equations. So kinematics is that branch of mechanics that describes motion that occurs when acceleration is constant. And let me just remind you what the word constant means in physics and math. Constant means that a quantity is not changing in time. So if acceleration is constant, that means that acceleration is just equal to some number. And the instantaneous acceleration equals the average acceleration because it's not changing. So a is just some value. Maybe a equals 3 meters per second squared. Or a could equal 0. 0 is also a constant number. The point is that it doesn't depend on time. So when this is the case, it's not generally the case in nature, but it's often the case in physics and engineering problems that we'll encounter, then a graph of acceleration versus time would just be a horizontal line where this value is your constant value of acceleration. And that means that velocity also looks like a straight line where the slope equals acceleration. And you can take that one level further and look at the position versus time. That will look like a parabola. So these are the general shapes of acceleration, velocity, and position that are always true when you have constant acceleration, or when you're in this situation of kinematics. These relationships come from calculus, and we're not doing calculus in this class, but it's not that hard to derive these relationships. From these relationships, we can write down a set of 4 kinematic equations. These are the equations that we'll be using all the time. So let me write them down now, and in the next video and in many videos and lessons and homeworks and quizzes after that, we'll be applying the kinematic equations to all sorts of situations. So let me show them to you now, and then we'll do some examples. Okay, I like to write 4 kinematic equations. Your textbook, I think, writes 3, but they can all be derived from one another. So here's the first one. It says V final equals V initial plus acceleration times time. Second kinematic equation, X final equals X initial plus 1/2. V initial plus V final t. Third one, X final equals X initial plus V initial t is 1/2 A t squared. And last one, V final squared equals V initial squared plus 2A X final minus X initial. So a few things about these equations. First of all, they come from somewhere. They come from the calculus definitions of position, velocity, and acceleration. So you can derive them if you use some calculus. We won't derive them in this class. I'm just presenting them to you, saying this is what they are. And this is Spike. He likes the kinematic equations. You don't have to memorize these equations, but I bet that you will have some of them memorized by the end of this class because we're going to use them all the time. Another thing to point out is, as I've been mentioning periodically, these all involve, initial and final quantities, and whenever you're solving a problem, you have to keep in mind what we mean by initial and final states. It depends on what the problem's asking for. And sometimes you see these written slightly differently. Keep in mind that we learned this definition of displacement, that's x final minus x initial. So sometimes people write the kinematic equations with displacement instead of these x finals and x initials here. So with this notation, they will look like the following. The first equation is unchanged. In the second equation, you can put x initial to the left side of the equation. So you get x final minus x initial, which is delta x. You can do the same thing in the third equation. Put x initial over on the left side. Delta x equals v initial t. It's 1/2 a t squared. And in the final kinematic equation, you can replace this quantity in parentheses with delta x. All right, next videos we'll start doing some examples of